see overview of parallel merge sort. Parallel merge sort is a divide and conquer sorting algorithms optimized for parallel processing. It splits an array into smaller parts, sorts them concurrently across multiple processors, and merge them back. This makes it highly efficient for large data sets and useful in high performance computing areas like scientific simulations and big data analytics.
Next, we have work and span analysis. In parallel computing, work, or we call T1, is total operation if we use only one processor, while span, T infinite, is the time takes it with an infinite number of processors of the critical path. For example, in our parallel merge sort, work is approximately called O and log n, and span is O log n. This shows how the algorithm scales more processor means shorter execution time, but only to a certain limit due to dependencies in the merge step.
So here we compare the theoretical and measure values for parallel merge sort using an array of 8 elements. Theoretically, we accept the recursion depth of span to be log base 2 of 8, which give us 3 steps. At each level, merging takes linear time, so the total work is around 24 operations. This gives a parallelism value of 8, meaning the algorithm can be up to 8 times faster with enough processor. When we run the actual code, we track the total number of operations using an operation counter. The result was 41 operations, and the recursion depth still match the expected 3 steps. This gives us a measured parallelism of 30.67, which is even better than the theoretical estimate. It shows how real implementation can reveal deeper optimization potential compared to the theoretical estimates.
Here is a simplified version of the pseudocode for the parallel merge sort. The parallel merge sort function recursively divides an array and tracks the depth of the recursion. The merge function combines two sort array and update the operation count, which represent the total work is done. This global variable operation underscore count for the work and max underscore tab for the span help us to measure the performance characteristic of the algorithm. So next we have implementation of the pseudocode algorithm in the C++. This program sort an array and claim the total number of operation and the maximum depth recursion. For our test case with the 8 element, the algorithm performed 41 operation and reached the recursion of depth 3, which is our span. From this, we calculate parallelism 41 divided by 3, which gives us around 13.67. This tells us the algorithm has strong potential of speed up when run on multiple processors, assuming a minimal overhead.
On the next part of the slide, we'll be covering on Amdahl's law, the concept of span as a limiting factor, and practical performance and overheads in shared frameworks. So for the Amdahl's law, it is formulated by Jean Amdahl that tells us the speed up of a program is using multiple processes. In parallel, computing is limited by the time needed for the sequential portion of the program. This means that not every part of the program can be perfectly parallelized. Some parts must run sequentially, which one step after another. Amdahl's law quantifies how this sequential bottleneck affects this overall speed up we can hope to achieve even with an infinite number of processes. So for the formula for Amdahl's law is speed up equal 1 over 1 minus p plus p over n. 1 minus p indicates the sequential part of the program, while p means while P is the portion of the program that can be parallelized, and N is the number of processes. From the analysis of parallel merge sort in previous part, we calculated total work equals to 41 operation, span is 3 step, we get parallelism for 13.67. This indicates that the algorithm can achieve up to 13 times speed up with enough processes. The span is the limiting factor as it represents the longest chain of tasks that must be run sequentially, regardless the number of processes. A long critical path limits the overall program speed, regardless of processes we add. To improve this parallel performance, we need to shorten the critical path as much as possible. Next is practical performance and overheads in shared frameworks. The first one is synchronization overhead. In parallel merge sort, threads must wait at each merge level until both subarrays are sorted. These waiting periods introduce idle time and reduce CPU utilization. Second is communication cost. In shared memory system, threads often share data structures and need to manage cache coherence, which introduce latency. Memory bandwidth becomes a limiting factor, especially during the merge phase for large arrays. And the third one is thread management overhead. Creating and destroying threads incurs costs. If these costs aren't managed efficiently, for instance by using thread pools, they can outweigh the benefits of parallelism. And the last one is load imbalance. Imbalanced task distribution or data dependent operation can cause some processes to work harder than the other's processor, which reducing efficiency.
This slide explains key concept in parallel algorithm. Work is the total amount of computation and span is the minimum time needed if we had unlimited processes. By analyzing this, we can see which part of a program can run in parallel. If the span is short, we can get more speed up. But too much parallelism can cause problems like communication delay and synchronization issues. So the goal is to find a good balance between speed and coordination cost. Okay, thank you.